start by saying thank you for our next speaker for all of his sleepless nights, whether he's paid for it or not. He's here to give this to all of you. Thank you.
Thank you. Appreciate it.
Have one.
Thank you.
Don't let me forget my camera. There we go.
1, 2. Okay. Okay, it works. Clicker test, clicker test, clicker test. Our story begins on March 14th, 2025. At about 4 p.m. UTC, an attacker was able to compromise a popular GitHub Actions repository called TJ Actions change files. The attacker injected code to the repository that was printing all of the CI runner's secrets to the CI runner's logs. About 4 hours later, the first issue was created on GitHub, pointing out that something odd was going on in this repository, and that consumers of it were getting their credentials leaked. The following days were a mess in the GitHub Actions ecosystem. We had companies trying to warn users against using this action. We had CVEs being created. And overall, fear was sown among the GitHub Actions users. Everybody posted about the leakage and that TJ Actions was compromised. However, this was not the attack. The leakage was not the point of the attacker here. So, my name is Aviad, and welcome to today's talk, not just a pipeline leak, reconstructing the real attack behind the TJ Actions incident. A word about myself. My name is Aviad Hahami, previously a security researcher at Palo Alto Networks. I'm currently an eBPF engineer at Adigos.io, and I'm interested in bug bounty, graph theory, lactofermentation, and other stuff. Right before I start, I'd like to say two things. First, parts of my family and my parents are here, so they came all the way to DefCon. Thank you. Here's the voice crack. They came all the way to DefCon. Last year, they didn't believe I gave a talk here, so they had to see it in their own eyes. Thank you for coming. This is exciting. I really appreciate it, and I hope you last past slide number 4. Second, my wife and a group of my friends sit at my house now watching this. Here's a drinking game for you and for future YouTube viewers. Whenever I say TJ Actions, take a sip. I'm an alcoholic, trust me. All right. Okay, focus thing. Okay. So, as I just said, at the time of this research, I was a security researcher at Palo Alto Networks, but no more, so I'm going to read this one. This presentation covers research performed by my colleagues and myself during my time of employment at Palo Alto Networks. I have since left the company and no longer work for Palo Alto Networks, and therefore I'm not speaking on their behalf here today. I would like to thank Palo Alto Networks for allowing me to share this research with the community. All right. Cool. So what's in this talk? This talk is going to be a debug level walk through the TJ Actions incident. We will uncover the end-to-end attack flow and track the timeline of it. We will go over the TTPs the attacker employed and break them down in order to get a better understanding at our ecosystem and its vulnerabilities. We will then go over how we at Palo Alto Networks were able to trace and uncover the steps of this attacker and what tools we've utilized to do so. I'll then share some additional victims of this attacker and the impact, and wrap it up with some mitigations and a brain teaser, something I'd like to ask you all and share with you. So, as I said, our story, the TJ Action story, takes place in the GitHub world, where anyone can make their code accessible to others. We know this today as the open source community, which we learned to rely upon and trust. We trust it so much that we have complete ecosystems rely upon that. A quick and easy example is the Golang ecosystem, right? And within GitHub exists a CI/CD offering called GitHub Actions, which allows users to execute arbitrary code from other open source repositories. In that context, such repositories are called actions, and by referencing them in our CI pipeline, we allow GitHub to execute the actions code in our context and perform various tasks like build, lints, tests, you name it. And if you're curious to know how many engineers and developers actually rely on running arbitrary repositories code in their pipelines, then a recent paper showed GitHub Actions is said to be used by at least 33% of the market. I did see some papers stating more than 50%, but it seemed a bit like non-realistic, so I went with a more conservative paper. And throughout the years, we as a community, we developed a habit of assuming that if something is accessible to us and it's accessible to the masses, we can rely upon it. We call it highly eyeballed, well opinionated, we give it names, but basically it's accessible to the masses, so we trust it. We actually trust it with our most sensitive processes, like building our product. And attackers know that fact too. And when such a trust contract is breached, we get the following news. 23,000 projects getting their credentials leaked to random people online. And while this is a severe thing, I agree, I just said a moment ago that this was not it. This was not the attack. And in reality, this was just the tip of the iceberg, the nuke, if you will say, at the end of the line. So let's start breaking down this attack. When we initially faced the attack, we were met with the following scenario. We had an attacker that somehow compromised the TJ Actions changed files repository. And this repository happens to be a popular GitHub action that was used by many GitHub Actions users in their workflows. And during the time of this event, whomever used this action got their credentials leaked. Pretty simple. When I say, by the way, a workflow that it was used by many, then it implies you had or others had this type of workflow definition in their repository, either public, private, you name it, and you were basically referencing the repo TJ Actions explicitly, like we see here. And if you see it references v39, so it implies I want this repo at git tag v39. That's basically it. When you have that in your pipeline, you basically you say, hi GitHub Actions, run the code in this repository in my context, right? That said, after the initial facing, 2 weeks after, we were able to draw this diagram. This was created by my team and myself, and it's a much more complex diagram. It contains many more steps than what we initially thought happened. I probably look like this with the slides behind me, with everything with all the arrows. So instead of where we started this quest, which is from the highlighted part of this diagram, in this talk we will actually start from the beginning. We will start from the attacker's position. By doing so, I'll be able to explain the TTPs in a constructive and progressive way, and we'll be able to draw the complete events timeline in a coherent and continuous way, and I hope things will make sense. Once done, I'll discuss what tools we've utilized in order to be able to reclimb that tree and draw everything that you saw on the diagram. Thank you for the other hole. So let's clear the board. We will use the diagram as our quest map. And at the bottom, between each movement of the attacker that I'll highlight in the quest map, I'll display a timeline and we'll put a point on for each event. We can actually start and add what we already know. This is March 14th, 2025, the mass credential leakage. That's on the right-hand side. Let's put our attacker on the board. They're going to be on the left-hand side. And now let's see how the attacker finally reached the TJ Actions repository. First move by the attacker, compromising the Spotbugs organization. This is the first move. This is what initiated everything. Let's see what they did. In order to do this step, the attacker employed a TTP called pawn request, poisoned pipeline execution. And this is when an actor can run unauthorized code in your CI machine. Basically a CIRC if you'd want. So let's visualize that. And there are many options. So I'm going to show you the one the attacker employed. Assuming you have this GitHub setup, you have your GitHub Actions CI set up, and you have your repo A. And let's also assume that somebody forked your repo. Then this is their position now, the attacker's repo. From this point, there are, again, many variations to perform a pull request, but what our attacker did was create a malicious commit inside the fork and create a pull request. In response, the victim's CI got triggered and executed. Now, during the vulnerable execution of the CI workflow, it checked out the code from the fork repo. This is because of misconfiguration. This is this specific variation of pull request, and executed the malicious code in its context. And now you have a malicious code executed in the context of a victim's repository, and you could do many things, like in our case, exfiltrate all the secrets that are accessible to this machine. Let's see this TTP employed by our attacker. So using this technique, the attacker targeted a vulnerable GitHub Actions workflow in an organization called Spotbugs, specifically in a repository called Sonar Findbugs. Here we can see the pull request of the malicious commit that the attacker created in their fork. All the attacker actually did was introduce a single line change inside the Maven W file, which was later executed in the CI workflow. In the change, we can see a curl to fetch a bash script from the attacker's repo, piped to bash for execution. Everything is being, all the std out, std are being redirected to dev null, so everything is muted as well. And that was it. That's all the attacker had to do. Now, this event took place on December 6th, 2024. That is more than 3 months prior to what we were told about the TJ Actions incident. And the result of this exploitation was a personal access token, a PAT, of a maintainer, a Spotbugs maintainer, that the attacker was able to leak. I'll mention that if a PAT gets stolen, as long as the owner does not revoke it, it's like usable. It contains all the permissions the owner gave the PAT. And throughout this attack, this token was accessible to the attacker because the owner just didn't know. So we have this PAT in hand. Let's pop back our diagram. Here's our attacker, and here's the Sonar Findbugs repository. And since the attacker collected a PAT by exploiting the pipeline like we just saw, the attacker now have admin access to Spotbugs organization. Do note that the stolen access token had access to more repositories than what is shown on the screen, but I am only showing the repositories that took place throughout this attack. Let's see the timeline. So we had on the right-hand side March 14th, mass credential leakage. And on the very left-hand side, we have Spotbugs getting compromised. Let's move on. The second step of the attacker was recon and waiting. In the time following the attacks on Spotbugs, the attacker used the stolen PAT they obtained for sniffing around and checking what other organizations and repositories they could access using that token. We only know that because of the help we got from the maintainer of Spotbugs, who was kind enough to share their activity log with us. And I'd like to share something interesting that we could draw. So actually, it was deleted, so I wouldn't share that. But here's an example of one of the things the attacker was able to find. Inside the repository Spotbugs, which the attacker can now control using the stolen PAT, existed another interesting PAT. The attacker found out that there was another Spotbugs maintainer, and not the previously mentioned one, which had their own PAT being used as a secret for the GitHub Actions workflows of Spotbugs. What made this specific PAT interesting to the attacker is that this maintainer was also a maintainer of another organization. And this organization is called ReviewDog. Remember that fact, we're gonna meet that in a second. And thank you. And for the second phase of step 2, all the attacker did was to wait. The attacker didn't exploit anything or performed any known lateral movements, although they technically could. They had the credentials, but they didn't do anything. And 3 months after that, after the compromise of Spotbugs, the right target showed up. The whale surfaced. The attacker waited and waited. And then on March 7th, a Coinbase maintainer pushed a GitHub Actions workflow that utilized the TJ Actions changed files repository. And that is when our attacker started moving, and moving fast. In practice, the attacker moved so explicitly and boldly towards that Coinbase repository that they were basically admitting, along some other IOCs, we will see indications of compromise we're going to see ahead, that Coinbase was the only thing that they were interested in throughout this attack. Let's put this date as well on our timeline, and this is March 7th, 2025. Coinbase becomes vulnerable. Now for the fast movements. Step number 3, lateral movement into the review dog organization. As I just showed you, during the recon phase, the attacker found out about the path of the review dog maintainer existing within Spotbugs. This token was the key into moving into review dog. And in order to exfiltrate this new path, the attacker had to interact with the codebase. This is because they can't just use the path they stole to access to GitHub. It doesn't work like that. They can't click and view the secrets. GitHub hides that on their UI. So the attacker had to extract the token in a different way. Now, obviously, since the attacker had write permissions to Spotbugs, they could simply push a malicious workflow, right? They could do that. They had write permissions, and it would exfiltrate the token. But such a push makes a lot of noise. So if the attacker would do that, they would either push a new branch with a commit, which makes a lot of noise, or push a commit to another branch, which also makes a lot of noise. So what did they do here? Let's see that. Yep. TTP number 2, this is memberships and disposable users. So this was the attacker's solution for this situation. In order to stay under the radar and not raise suspicions, the attacker created a dumb user called Jurka of Avak. I'm only mentioning that because at the time I tried to find what the hell that means. It's something anime, I believe, but I wasn't able to decide on that. And they invited this user to be a member of the Spotbugs repository. Using that user, the attacker pushed a branch with a commit containing a malicious workflow that exfiltrated the said path. And once the workflow was triggered, the Jurka of Avak user deleted itself and the branch. Now, this may be a bit complex. Let's see that visualized. So we're going to use a sequence diagram. We have at the top the attacker, Jurka of Avak, and the Spotbugs repository. We have step 1, the attacker invites as a member the user. Step number 2, Jurka of Avak, basically the attacker, pushes a branch with the malicious workflow to Spotbugs. The CI of Spotbugs kicks in, executes the malicious commit, and roughly at the same time, Jurka of Avak deletes the branch and itself. Let's see the artifacts of that. What we have here is the activity log of Spotbugs. This is public. You can check it afterwards. And we can see that a branch was created and deleted. We can see at the top the branch name. This is just gibberish, whatever herbekerbe, whatever that means. And if we would inspect the timelines, we will see the timestamps of these events. We will see that they happened within the same minute. So pretty fast movement. This is the malicious workflow that the attacker pushed. If we zoom in, this is the workflow's trigger. So basically on push to this specific gibberish branch. And the rest of the workflow, the payload, may seem a bit fancy. We're going to break that down, but it's pretty standard in the exfiltration world. Let's take a look. So at the top, we have the attacker taking all the secrets that are available to the machine and stringify them. They move on to generate an asymmetric AES key, encrypt the file with the secrets, and they move on to encrypt the encrypted secrets and the key with their own public key that they hard-coded, and they uploaded this whole thing as a GitHub artifact so they can download it after. Now, since everything is encrypted, even if you would see that online, you wouldn't be able to decrypt that, right? So this is how it's being done in the GitHub world. Now, not only the attacker, by exploiting this workflow, not only the attacker obtained a new path and was able to move laterally now into review dog, By performing the exfiltration using this technique, the attacker left minimal footprint, which made detecting the exfiltration a lot harder. Let's go back to our quest map. This is where we left our attacker. They can access podbugs. And in the newly highlighted part, we can see what our attacker did using the dummy user and the malicious workflow they pushed. And once the deed was done, a new access token was obtained, a path for review dog, and the attacker's domain expanded. I really hope someone is catching that reference, but yeah. Anyways, now in the highlighted part, we can see the new options that the attacker unlocked, and we can see on the right-hand side the review dog action setup repository, and that the attacker can access it. Again, the attacker could access many other repositories, but this is the one that mattered. Let's move on to the next step. Step number 4 of the attacker, lateral movement into the TJ actions organization. Okay. So this is the attacker's current position, and as I just said, the attacker is about to move into the TJ actions organization. Highlighted in blue, you can see a dependency chain that the attacker is about to compromise, where we can see that review dog action setup is a dependency of an action called TJ actions ESLint changed file, which is used in the repository TJ actions changed files as an action. I remind you that the attacker already has an access token to the review dog, and again, they could just push a malicious commit and infect this whole chain, but instead, they did something different. The attacker employed a very interesting technique here, which in my opinion is the most interesting one throughout this whole attack, and it is abusing one of GitHub's core features. Let's see what the attacker did. TTP number 3, we're going to give it another name in a second, but for commits and git tags. So on GitHub, when a repository is forked, it is added to the so-called fork network of the original repository. However, this is a GitHub feature, not a Git feature. Git doesn't have forks, it has branches. So behind the scenes, forks are pseudo branches or whatever it was wrapped in the GitHub backend, but it's just a branch. So a residual artifact of that is that commits that were pushed to a fork are accessible from the main repo. Okay, so you can go afterwards and check it, make a fork, get your own repo, and try to access a SHA from that fork, and you'll be able to see that from your main repo. Now this, when combining it with git tags, is an interesting thing, but I just want to add that in other words, committing to a fork is equivalent to pushing a branch to a repository you don't own. The code doesn't do anything, but it's there. Let's combine that with git tags. So when combined, it creates an interesting behavior. If you don't remember for some reason, git tags are just pointers to commit SHAs. So assume main branch. Consider this main branch on some repository, and let's assume that it was forked, and a malicious commit was pushed to that fork. According to what I just said about the commits inside forks, in GitHub, all of these are roughly in the same, we can say in the same context, on the same repo's context. So with respect to git tags, if I have a git tag pointing to a commit SHA, for example, commit 2, as seen in the diagram, nothing stops me from making that tag point to a commit from a fork. This TTP is a well-thought one, actually, because it achieves two things. One, no commit noise. Nothing was pushed to the repo. Complete silence on that end. And second one, this is a GitHub audit log blind spot. It does not get logged there. And without help from GitHub support, which they can obviously give you the ref logs, the Git ref logs, without them doing that, you won't be able to see these events. So the attacker utilized this technique multiple times in the steps ahead, and we're going to refer to them as shadow commits. And let's see them in play. So back to the diagram and the about to be exploited dependency chain. Let's remove the highlighted part and make the attacker earn it. So for this step, the attacker created a fork of the review dog action, the action setup repository, like we saw happens in the shadow commit TTP. And then they push the following commit to it. This is that commit. It's another weird-looking username, ILM, whatever. We used to call that Irma during the investigation. And we actually used to call it Irma. And if we will expand that diff, we will see a base64 encoded string, which decodes to a Python program. We're going to see that in a second, and some script underneath that. Let's look into them. This is the same diff with the Python base64 decoded. Let's zoom in. Here we can see the Python script. It's a bit small, but I'll tell you that it is looping over the procfs file system. It extracts the maps and the memory of the processes it found. And down the line, it basically prints them to the standard output. Now, on the second part of that script, we can see the snippet obviously decoding the base64, which I've done for this talk, writes it to a file, makes Python execute it, takes the outcoming std out, pipes it, does some filtering, some cleanups, and prints it to the log. Now, this may be a spoiler, but this is pretty much the same code that later landed in the 23,000 repos. So once our attacker had this commit in place, we're in the shadow commits TTP. Once the commit was in place, they override the tag v1 of review.dog action setup, making it point to their malicious commit. We can see that highlighted. And let's put that as well in our timeline. This is an important event. This was March 11th, 2025. By doing the override step, our attacker poisoned the v1 tag of the review.dog action setup with minimal footprint. And per our chain, since TJ Action's ESLint change files was referencing the v1 tag of the action setup repository, it was now infected as well and was shipping the malicious code to its consumers. Among its consumers, the repository TJ Action's change files was a consumer of it, and this action ran as a part of its CI. Now, this didn't happen yet. TJ Action's change file wasn't compromised yet, but the attacker was staged to do so. So all they had to do now was wait. And we know that the tag was pushed on 6:42 p.m. UTC on March 11th. And we found out that the tag was reverted to its previous value by the attacker, of course, less than 2 hours after the infection. That was 8:31 p.m. UTC, basically marking that the attacker was now inside TJ Actions and they didn't need the review.dog infection no more. All right, since TJ Action's change files ran the malicious code, the CI picked it up and ran the malicious code. All the secrets that were present on that machine were leaked and compromised, were leaked to the attacker and compromised. And by that, our attacker obtained another set of access tokens with permissions, and this time to TJ Actions. Let's put this event in our timeline as well, and let's move on. This is still March 11th, and TJ Action gets compromised originally. With our attacker stage at TJ Action change files and with full control over it, it was time for the attacker to infect the actual target, Coinbase. If you're unfamiliar with Coinbase, Coinbase is a NASDAQ-traded crypto platform with a market cap of $106 billion. Suddenly this attack makes sense. It allows users to buy, sell, and store digital assets like Bitcoin, Ethereum, or whatever coins, using self-made tools like the highlighted repository AgentKit. Specifically, this repository is described as every AI agent deserves a wallet. If you'd like to hear my rant about AIs, come meet me later. So this repository, as I said before, was using TJ Action's change files, and that was the target of our attacker. Let's see what they did. Using the same TTP of shadow commits, the attacker created a fork of the repository TJ Action's change files and overrode the tag v39. This is highlighted. This event takes place on March 13th, 2 days after the review.dog infection and less than a week after Coinbase got into a vulnerable position. Let's add that as well. This is the commit the attacker made throughout the shadow commits TTP. We can see highlighted again, a curl bringing some script, and then later being executed by Python. But what's more interesting here than this payload is the smoking gun. We can see here the attacker explicitly and hard-coded the name of Coinbase and said to the machine, if you're not in Coinbase, and there's an OR, if you see there, the OR is to one of his dummy users. So if you're not in Coinbase or in my place, you execute. So even if you would use one of the malicious versions, if you're not Coinbase, you wouldn't get the impact. But that is a nice smoking gun. So with a committed tag in position, our attacker again had to wait for a CI machine of Coinbase to pick it up. And eventually it happened. On March 14th, 3:10 p.m. UTC, a CI machine of Coinbase picked up the malicious action, and the credentials and secrets that were present on that machine got leaked to the attacker. Let's add that to the timeline. I decreased the size of the previous events to make some room. And let's look at some indications of compromise. This is how the CI log of the infected machine of Coinbase looked like. We can see in the upper right the permission the execution had, like write permissions for deployments or contents, which implies you can write to the repo. And in the lower highlighted part, you can see that the SHA of the malicious commit, the malicious commit the attacker made, you can see that it was fetched when the Coinbase machine tried to fetch v39. So instead of getting the actual v39 commit that was pointed to, the machine got the malicious version. Back to our attacker. After about an hour after Coinbase got compromised at 4:37 p.m., Coinbase was notified that there is some suspicious activity in their CI pipeline. And they immediately identified that it was coming from the TJ Actions usage and removed the workflow that used TJ Actions. And at once, the link our attacker was building towards was deleted. Coinbase was no longer accessible for our attacker. Now, we assume the attacker noticed that the link was deleted because this is a great segue to what we're going to see next. 20 minutes after the attacker lost the link to Coinbase, they decided to go all out and burn the field. They basically Leroy Jenkins'd everything we're going to see. On March 14th at 4:57 p.m., the attacker performed the last shadow commit maneuver, and the attacker overrode most, if not all, of the tags of TJ Actions change files, made them all point to the malicious commit they created with the secret logger that I showed you before, that was printing to the logs. By doing that, the attacker basically nuked everything, and we are arriving to what we learned to know as the TJ Actions incident. Again, as you saw, this was just the tip of the iceberg of this thing. And it took us some time, but we were able to track the steps of this attacker, draw the complete attack flow diagram, and I hope it was clear, and I'll stop seeing comments like this on Reddit. So I'm aware this is a lot to digest, and let me show you some pictures from behind the scenes. This is how one of the boards in our office during the investigation. This is my personal notepad where you can see some classic coffee stains on the left-hand side, and was few all-nighters, fun times, great CTF, honestly. And let's go over the TTPs and put them in a list so we can understand what exactly happened here. So list of TTPs. We got one, shadow commits abusing GitHub's fork network in order to introduce code changes to a repository's context without making actual commits to it. We got two, tag overrides abusing GitHub's audit log blind spot and silently redirecting consumers to different commit SHAs. We have three, the disposable members, where the attacker made the noise be associated to a disposed user. And last and not least, PON request, RC, and CI workflows due to various misconfigurations. Now, towards the end, we're getting there. I want to share how we conducted this investigation. So as I said, we began here in the highlighted part, and we had to climb back this whole chain and find all the evidence. So we've used the following tools. We heavily utilized the GitHub events dataset on ClickHouse. This is, if you're unfamiliar, a great SQL queryable tool based on the ClickHouse infrastructure, blazing fast, free. But however, it doesn't always contain all the information that we needed. So in order to get a better resolution and at specific points. We've used the GitHub archive. I saw it was referenced here yesterday in one of the talks, so it is a great tool apparently. It allows you to download the logs of most GitHub events in a resolution of 1 hour. Comes in handy in cases like this. Thank you for that project. And in addition, we communicated with all the involved maintainers, and they were very kind and helped us draw the picture of this attack as we saw today. Great community. One shout out I would like to make is to Adnan Khan, who tweeted this amazing lead during the investigation. There was a lot of discussions on X during the investigation, and this was a great breakthrough. I know Adnan is not in the crowd right now because he's giving a talk at 1 p.m. On the Creator Stage 5 alongside Looping about advanced offensive strategies in the supply chain ecosystem. I highly recommend that one. Now for additional victims and impact. We observed that the attacker tested various payloads against a fork of Ultralytics, and that was done 3 days after Ultralytics was breached on December 4th, 2024. We saw the attacker was testing with some payloads, but we didn't find any impact, although we saw the payloads. In the same fashion, the attacker played with a fork of Apache Superset. This is a data visualization framework, 67.3K stars on GitHub. Yet again, we didn't find impact. We didn't detect. That said, the next repo, Module Federation Core, which is, according to them, concept that allows developers to share code across multiple JavaScript applications. We did see the infrastructure for the shadow commits being made, but we didn't see any logs and indications of compromise. So we did see the things, but we weren't able to confirm that. So we're uncertain. And for the last repo by Baidu BCE, which is a one-stop shop for AI native applications, we were able to detect malicious pull requests, and we know for a fact that their pipeline was compromised. Quick words about mitigation. Here's the list again. Let's go one by one. So shadow commits, if you have forks allowed in your repo, you are opted in. Nothing you can do. Tag overrides. You'd be happy to hear that GitHub is testing with immutable releases and tags. This feature means that once you make a tag or release, they're immutable, they're pointers, and they will be immutable. This may be GitHub's takeaway from the post-mortem of this. I only know this because I stumbled across this LinkedIn post by a GitHub product manager, says she's in charge of the supply chain security at GitHub. You have at the bottom the QR to go to that post. And in one of the comments she made, I found a link she shared to a gist of hers with details and specs of the immutable releases feature. The moment I saw it was marked as a secret, I forked it, and you can access it here. Why not? Per the PON request, this is a well-covered topic in various ecosystems. This is a list of tools that can help you audit your pipeline, basically. And the last mitigation advice here would be to stop the bad practice of using Git tags in GitHub Actions. It was covered previously many times. Most of the community still does that, so thank you, Biden. Don't use that. And instead, prefer 40-char Git SHA, a complete one. Before I seal this talk with a brain teaser, I'd like to thank my colleagues at Palo Alto Networks, to Yaron, Asi, Omer, and Gil. Thank you for your part in this research and being amazing colleagues 24/7. Then I'm annoying as hell, so 24/7 was needed for me. And now for the last outstanding question with this research, something I'd like to send you home to think about. Let's zoom out and look at the complete diagram. We saw that the attacker executed a well-planned attack. They had time during the execution. They used various techniques while executing it. Some are more impressive than others, I agree, but still various TTPs. And they moved very fast once Coinbase was vulnerable, right? Now, with respect to that, given that this was the final exploit of the attacker, an open source Python memory dumper that simply logs to the console and gets downloaded on each CI machine that is infected. That makes a lot of noise. They didn't make the script call home at the final exploit like they did on Coinbase. They could have, they didn't. They did make the network noise though. And they didn't double encrypt the stolen credentials like they did for ReviewDog. They could have, they chose not to. Instead, the attacker simply printed the secrets to the logs of 23,000 repos. That's a lot of credentials, a lot of potential money, and a lot of potential further lateral movement. Instead, the attacker printed it to the logs. Logs are noisy, downloading in your CI stuff is noisy, so my question with respect to this whole research is, why did the attacker choose to make that noise? The attacker eventually pushed a commit. It was a decision. It was an active thing. Why would they do that? Was this decision made by mistake? The attacker was nervous about getting caught and bailed, or they didn't have a proper exfiltration in place, so they were unprepared for that masses of credentials? We saw the TTPs, it doesn't really make sense. Or was it on purpose? They purposely tripped the wire, they made the noise. What would be the reasons for that? Was that in order to make GitHub stampeded GitHub support? Getting 25,000 Zendesk tickets can kill someone, so maybe they just wanted to block GitHub support? Or maybe it's an upcoming APT just trying to gain some street cred, but then we're lacking the attribution. They didn't post anywhere who they are. So these are open, and there's another hypothesis saying, what if there is a buyer and a seller here, where the seller found the Spotbugs token, sold it, and the second actor was not as professional. We did see a breach forums post on that on the PON request TTP, specifically mentioning Ultralytics, by the way, and that was the same month Spotbugs was exploited. So maybe it's related. So the last outstanding for me, and that is my final slides, thank you for your time. The last outstanding question for me is, why? Why would you do that? Here's a link to our complete article regarding this incident, more IOCs, more information, more complete timeline, how we exactly traced it back, because tracing it back was a bit more confusing and long. I would like to thank everyone who helped me make this talk. Especially to my wife, which at this point knows more about TJ Actions than I do. I was Aviad, find me on X. Thank you for your time. This is it. If there are any questions, I'll be answering them down here until we get kicked out and then outside. Thank you very much.